physics on ice skating.
Hi, I'm Carrie. I'm going to explain how we came about our problem for physics. We tried to think of something we could do, and we decided to do a problem with skating. Since I had skated for 15 years, and Joanna, who's supposed to come in, she works at an ice rink, so we decided to find the kinetic energy of me when I was spinning. When you start out spinning, you start with your arms out, and then to go faster, you bring your arms in. So we decided to find the initial kinetic energy of the skater when she has her arms out, and then the final kinetic energy of the skater when she has her arms pulled in.
So since we know that we're spinning on a vertical axis on a frictionless surface, we are using the total moment of inertia and angular momentum. And then the initial moment of inertia would be when she has her arms stretched out. And then the final moment of inertia is when she actually closes her arms and spins faster.
And then we found out that the inertia will be the inertia of Carrie and the inertia of the rice, since we're using kilograms of rice instead of dumbbells, so that they're easier to hold.
And to find the angular velocity, which is omega initial, you have to multiply 2 pi times 1 revolution per how many seconds it took for 1 revolution.
And then to find the initial kinetic energy, you multiply 1/2 times the initial kinetic energy times the initial angular velocity squared. And to find the final kinetic energy, you multiply 1/2 times the final inertia times the final angular velocity squared.
This is me spinning without the rice bags.
Every time, so much fun.
This is me spinning with the rice bags.
And then from the total moment of inertia and the angular momentum, we're actually going to use this equation right here, and that's with the rice factored into the moment of inertia. And we have 3 kilograms per meter squared for the moment of inertia for Carrie when her arms are outstretched. And then you have 2 rice bags, and they both weigh 0.907 kilograms each. And when her arms are outstretched, her wingspan was 0.8 meters. And then we got 4.16 kilograms per meter squared, or times meter squared. And then with the final moment of inertia, her moment of inertia when her body, when she brought her arms in, was 2.2 kilograms times meter squared. And then you still have 2 rice bags at 0.907 kilograms. And now that her arms are folded into her body, the width of her body is only 0.305 meters. And from that, we got 2.36 kilograms times meter squared.
So the whole point of the experiment was to find out the angular velocity, omega initial, and we found that by calculating how fast she did a revolution with her arms outstretched, and we used a stopwatch, and we found that it was 0.8 seconds. So we did the 2 pi, and we found out that it was this value, and we then solved for the final angular velocity, and we got 13.8.
To find the initial kinetic energy, we have 1/2 times the total moment of inertia, which is Carrie and the weight with her arms expanded, and times the initial angular momentum, which is where we got this number, we squared it, and then our total is 128.2 joules.
To find the final kinetic energy, multiply 1/2 times 2.36 kilograms times meter squared, which is the final inertia, times 13.8 squared, which is the final angular velocity, and we got 224.7 joules.
And we even have a special guest, Sasha Cohen, the silver medalist from the Olympics.
He almost slayed him.